Using a pendulum on Earth, we will be able to calculate the speed at which Earth spins. Due to the different reference frames the observers are situated in, the perspective of a rotating observer and a stationary observer on a moving object will differ due to the Coriolis effect. Here's a way of making sense of the Coriolis effect. When the moving red observer watches the moving yellow object, the observer perceives it to be directly in front of him the whole time, even though the observer traveled a greater distance than the object. The same longitudinal change from one point to another will require greater distance change for the observer than for the object. However, when the observer throws an object, both travel at the same horizontal velocity. The further the latitude is from the equator, the slower point on the latitude would travel, and the faster the object would seem to be traveling relative to the latitude. This creates the perceived curved path of the object by a spinning observer. The Foucault pendulum illustrates the Coriolis effect in the rotating frame of reference, as the pendulum seems to experience a force perpendicular to the direction of motion, which causes it to rotate slowly around the platform.
At first, let's try to solve the problem, find the speed of our Earth, in a geometric way. In this picture, P is the initial position of the pendulum on Earth. After a while, with the rotation of the Earth, point P moves to P prime, and line PM is a tangential line at point P. Line P prime M is a tangential line at point P prime. Here, xy plane is parallel to x prime y prime plane. We set xy plane so that PM is pointing to the same direction of PY. Then there will be an angle alpha between P prime M and P prime Y prime. In this picture, theta is the angular displacement resulted by the rotation of the Earth. Beta is the angle that stands for the latitude of points P and P prime. The angular velocity of the pendulum is omega. Omega equals to alpha over t. In the sector P prime PM, alpha equals PP prime over PM. In the triangle PMN, PM equals Pn over sine beta. In the sector P prime Pn, PP prime over Pn equals theta, and so alpha equals theta times sine beta equals omega t times sine beta. Here, omega is the angular velocity of the Earth. In this way, we can find the relationship between uppercase omega and lowercase omega. And lowercase omega equals uppercase omega times sine beta. So we can find the period of the Earth rotating with this formula, which is t pendulum equals t Earth over sine beta.
These are the variables for the vector solution. In particular, there are different versions of the quantities for the pendulum and the Earth. Lowercase omega is the angular velocity of the pendulum on the platform, while uppercase omega pertains to the Earth. Theta is the angle of the pendulum on the platform, while beta is the latitude of which the pendulum is located at. The top line represents the difference between the forces in two different reference frames. The vector F on the left represents the force seen by the fixed frame, and the m times vector A represents the force from the perspective of a rotating frame. First of all, the centrifugal force is negligible because the capital omega vector has a very small magnitude. The cross product of two vectors of small magnitudes results in a vector with an extremely small magnitude. Now the Coriolis force is the difference between the two different reference frames. The Coriolis force here is negative because a vector of an opposite direction is adjusted from a fixed frame to get to the rotating frame. Instead of in the top equation, there's a plus sign because the vector is adjusted from the rotating frame to the fixed frame. We then convert these into the alpha vector cross x vector because the linear acceleration vector is the angular acceleration vector cross the radius vector. And the second part, which is 2 times lowercase omega, the pendulum's angular velocity vector cross the velocity vector. The left part is converted into the right part. We then set the Coriolis force equal to the force on the pendulum. The reason we can do this is because the pendulum is rotating around the plane due to the Coriolis force. That means any additional tangential or angular velocity of the pendulum is basically a result of the Coriolis force caused by the Earth. So whatever effects imposed on the pendulum is equal to the Coriolis force of the Earth on the pendulum. Since the angular velocity of the pendulum on the plane is not changing, d omega dt will be a zero vector, and the zero vector cross vector x will be another zero vector.
Because the second derivative of theta equals to 0, we can get the first step here. Then we can convert the right-hand side to a vector form by transforming the cross product. Next, we can cancel the same parts from the two sides. We get the magnitude of omega sine beta equals to the magnitude of d theta over dt, which is the magnitude of lowercase omega. And similarly, we found the relationship between the two periods. T pendulum equals T earth over sine beta, and the result here is the same result we got from the first method. To find out how fast the Earth is spinning, measure the time it takes the pendulum to rotate one full cycle around the platform. Along with the latitude the pendulum is located at, the angular velocity the Earth is spinning at can be found. The Foucault pendulum in the Paris is located at 48 degrees 52 minutes, and it takes 31 hours and 50 minutes to complete one full rotation. And so we found the period of the Earth is about 23.976 hours. And then we can find the angular velocity of the Earth, the uppercase omega. It is about 0.262 radians per hour. And this is our conclusion.